Hello everyone. So in this one shot, I'm going to cover atoms, which is a part of modern physics. So I'll cover all concepts and derivation in this video. So first we go through the syllabus. So first we'll cover alpha particle scattering experiment, and then Rutherford's model of atom and why this model is not valid, and then the Bohr's model of hydrogen atom, which is applicable for isoelectronic species. Then we'll also see the derivation for radius of nth orbit of the electron, and also the velocity of the electron in the nth orbit and the energy of the electron in the nth orbit. And we'll also see the hydrogen line spectra, like all the series, spectral series, like Lyman, Balmer, Paschen, Brackett, Fund. Right, so let's start. And then let us come to the Rutherford's atomic model. So it is very important. So first of all, you must have studied about Rutherford scattering in your class 9th, right? So I'm not going into that detail, but let us see some important observation. So first of all, most of the alpha particles passes through the foil undeflected, right? So what does it mean? So there are lots of empty spaces inside the atom. So most of the alpha particles suffer no deflection, and there are several alpha particles reflected from their original direction by large angles, right? And very few are observed to be reflected back, reversing their direction of travel. So what does it mean? So if they are completely rebounding, so if you take a case of a ball, if you're throwing a ball on the wall, what happens? The ball just rebounds back. Same is the case, and there will be some alpha particle which rebounds back. It means there must be something dense present in the atom, and that dense entity is nothing but the nucleus. So we can see the majority of the positive charge of the nucleus is concentrated in the nucleus, and due to that dense positively charged entity present in the atom, the alpha particle experience strong electrostatic repulsion, and it completely retraces its path. So what you have to remember? So you have to remember this graph. So on the y-axis, we have the number of particles which are getting scattered, number of alpha particle, number of scattered particle, and on the x-axis, we have angle of scattering. Now, what is angle of scattering? Suppose if this is the alpha particle, it is coming in this direction, and here we have the nucleus. And suppose this alpha particle deviated like this, right? So this is the velocity after scattering. So what is the deflection produced in the alpha particle? So we can find the deflection produced. So this angle is known as the angle of scattering. So this is angle of scattering. So if we plot this graph, so experimentally this graph comes out to be proportional. So this n will comes out to be proportional to 4th power of cosecant theta by 2. So do remember this proportionality. There can be a question based on this proportionality. Right. So now, what are the inferences of this particular experiment? So first, the positive charge in the atom was concentrated in the region that was which was very small in comparison to the size of the atom. Right. And this positive charge is known as the nucleus, and electrons are moving in a large volume of the atom outside the nucleus. So these are the inferences of the Rutherford model. Now there are some like phenomena which Rutherford was not able to explain, and first is it can't explain the line spectrum of the hydrogen atom, and according to Rutherford, it should be having a continuous spectrum, because when a charged particle is accelerating, it keeps on radiating energy in the form of electromagnetic radiation. So if that is happening, we should get a range, we should get an entire spectrum, rather some discrete wavelengths. So it was not able to explain. If you want to go through the justifications, read this, you will get the idea. So I'm not going into that detail. So it could not able to explain the stability of the atom. So again, if the electron is radiating energy, it will lose energy, and ultimately it will bombard on the nucleus, but we know atoms are stable. So these two important phenomena Rutherford was not able to explain. Okay, right. So what is this type of problem? Let us see. Suppose we have given an alpha particle, and this alpha particle has some initial energy Ki. Okay, and it is moving towards the nucleus, and this nucleus has an atomic number Z, and you can say the charge on this nucleus will be Ze, right? Now the impact parameter, or you can say the line of motion of the alpha particle passes through the center of the nucleus. And due to strong electrostatic repulsion, the alpha particle, let us assume that the alpha particle comes to for a momentarily rest at this particular point. So here the velocity will become zero. Now this distance is known as the distance of closest approach. And we are assuming that when the energy of the alpha particle was Ki, it was quite far from the nucleus. So they are not interacting at that point of time. So what is happening here? So there is a loss of kinetic energy and gain in the electrostatic potential energy. So if we want to find this R minimum, we can apply energy conservation. So if I apply energy conservation, so K initial, so this is the loss in kinetic energy, and gain in the electrostatic potential energy will be K Q1 Q2 by R, right? So K and Q here is charge of the alpha particle, and Z is the charge of the nucleus divided by R minimum. So from here R minimum comes out to be KQ ZE upon KI. Okay, so this formula you will get. So do remember this formula. Now let us see the application of that. An alpha particle with kinetic energy of 10 mega electron volt is heading towards the stationary point nucleus of atomic number 50. So what is the distance of closest approach? So we know that R minimum in this particular case will be K times Q times ZE divided by K initial. So K is 9 into 10 raised to power 9, and the charge on the alpha particle is 2 times the charge on the electron. So 2 times 1.6 into 10 raised to power minus 19, and the atomic number is given as 50. Again we have, so it will become E square, right? Divided by kinetic energy, which is 10 mega. So mega is 10 raised to power 6, and 1 electron volt is 1.6 into 10 raised to power minus 19 joules. 1.6 into 10 raised to power minus 19. So 1 E will get cancelled out. So we will have 9 times 2 times 1.6 times 50 into 10 raised to power minus 10 and minus 7. So let us simplify this. So this 2 and 50 will become 100. So we have 9 into 160 into 10 raised to power minus 17. And this comes out to be 144 into 10 raised to power minus 16, or we can say it will be 14.4 into 10 raised to power minus 15 meters. And we know that 10 raised to power minus 15 meter is nothing but Fermi, right? So we can write this as 14.4 Fermi. So that is the distance of closest approach in this particular question. Right. So now let us see the second problem type, which is based on the impact parameter. Now what is the impact parameter? Suppose this is the nucleus and this is the alpha particle, and the line of motion, if you look at the line of motion of the alpha particle, it is at a certain distance from the central line passing through the nucleus. Now the distance between these two parallel lines is known as the impact parameter, and this alpha is nothing but the angle of scattering, right? And that we have already discussed in Rutherford scattering case, right? So do remember this formula, which say where Q1 is the charge of the alpha particle. So let us say it has a charge Q1, and nucleus is having a charge Q2, and the initial kinetic energy of the alpha particle is Ki, and theta is the angle of scattering. Okay, so now let us see, so this K Q1 Q2 upon 2 times Ki times cot theta by 2. So let us see the question based on this formula which came in J. Now root D1 and root D2 are the impact parameter corresponding to scattering angles 60 degrees and 90 degrees respectively. When an alpha particle is approaching a gold nucleus, for D1 is equals to x times D2, the value of x will be, right? So here they have given impact. So basically we have to find the relation between impact parameter. So we are going to use this formula. So B is K Q1 Q2 divided by 2 times Ki cot theta by 2, right? Where theta is the angle of scattering. So can you see this factor is same for both the cases? So we can say B1 by B2 will be equals to cot theta 1 by 2 upon cot theta 2 by 2. So we can apply this proportionality, and B1 is given as root of D1 and B2 is given as root of D2, and theta 1 is given as 60 degrees, so it becomes 30 degree, and theta 2 is 90, so it becomes 45 degrees. So cot 30 is nothing but root 3 and cot 45 is 1. So now let us square on both sides. So this will become d1 by d2 is equals to 3. So x comes out to be 3. So 3 is the answer. Okay, now let us see the postulates of Bohr's model. So first postulate states that if we have a nucleus, positively charged nucleus, then the electron is orbiting with the help of the Coulomb attraction between the electron and the nucleus. So the Coulomb attraction is nothing but the agent which is providing the centripetal force. So Fe will be Fc. So we can say K times Ze times E by R square will be mv square by R. So we can apply this equation. Now the second postulate states that if the electron is orbiting in a particular orbit, then its angular momentum is conserved and it will be given by h upon 2 pi. So nh upon 2 pi. So this is the angular momentum, and we know if a particle is orbiting in a circle, then its angular momentum will be given by, in magnitude, will be given by mvr, right? So this is the angular momentum. So you should remember this equation also, mvn rn, where n stands for the nth. So nth with speed of the electron in the nth orbit will be vn, and the radius of the nth orbit will be rn, right? So nh upon 2 pi. And the third thing, when the electron is orbiting in a particular orbit, it does not radiate energy. It only radiates energy if it is coming from a higher energy level to a lower energy level. So suppose this is the nucleus, and let us say this is, say, second orbit, and this is the fourth orbit, right? So if the electron jumps from the fourth orbit to the second orbit, it radiates a photon of energy which is nothing but E4 minus E2, difference of the energies of the two levels. So do remember these three postulates. Now let us derive let us derive the radius of the nth orbit. So we are going to use the postulates, first two postulates. So according to first postulate, Fc is equals to Fe. So we can say m Vn square upon Rn will be equals to K times Ze times E divided by Rn square. So 1 Rn will get cancelled out. So we can write this as m Vn Rn times Vn. So this will be K Ze square. Okay. And we know that mv and rn is nothing but the angular momentum. So if the electron is orbiting in the nth orbit, so this will be nh upon 2 pi. So from this equation, we will get the speed, right? So we can say Vn will be kze square divided by nh times 2 pi. Okay, so if you look at the proportionality, so we can say Vn is equals to 2 pi ke square upon h times z by n. So Vn is directly proportional to the atomic number of the atom. It is inversely proportional to the principal quantum number, you can say n. And do remember this, Bohr's model is applicable for single electron species. So if I say, for example, let me also mention here, it is applicable for isoelectronic species like hydrogen is there, and then we have helium plus, lithium 2 plus, like this. Okay, so do remember this. And suppose if we are talking about lithium 2 plus, in that case the Z will be 3. For helium it will be 2. Right. So if you look at this vector, it has all known quantities, right? So K is 9 into 10 raised to power 9, E is the charge on the electron, H is the Planck's constant. So if we calculate, if we plug in the value, we will get Vn equals to 2.18 into 10 raised to power 6 Z by N. So you should remember this equation. So there are straightforward questions from this formula. Now we want to find the radius. So how we can find the radius? Let us substitute Vn in the angular momentum formula. So we can say m Rn 2 pi k E square upon h z by n times equals to nh upon 2 pi. So from this, let us simplify this. So Rn will be n square h square upon 4 pi square k E square m z. So can you see in the velocity formula, m is not there. So we can say Vn does not depends upon mass, but radius depends upon mass. It is inversely proportional to the mass of the electron, right? So we can say Rn is equals to h square upon 4 pi square k E square m n square by z. Again, there is a factor which contains known quantities. So if we simplify this, we will get radius of the nth orbit as 0.529 angstrom times n square by z. So do remember this formula. Okay. So this is the formula that you have to remember. And suppose if we have lithium 2 plus, then z will be 3. And if you want to find the radius of the third orbit, then small n is also 3. So like this, we can calculate the radius quite easily. So velocity we have already derived in the last section, that is 2.18 into 10 to the power 6 z by n. Now let us derive the kinetic energy, potential energy, and the total energy or mechanical energy. Right, so I need the formula for speed. So kinetic energy is half m Vn square. So if we substitute the value of Vn, we will get this formula, right? And if we plug in the values for known quantities, we will get 13.6 times z square by n square in electron volt, right? So 13.6 z square by n square. Do remember this formula. And potential energy will be given by k q1 q2 by Rn, or I can write with a or I can write the, let us put the charge. So Ze, and then it will be negative, right? K Ze square upon Rn. If you substitute the value of Rn, we will get Un, right? And it comes out to be minus 27.2 Z square by n square in electron volt. Now if we add these two, we will get this, right? So which is minus 13.6 Z square by n square. So do remember these three formulas. And if we substitute n equals to 1 in the mechanical energy, we'll get minus 13.6 Z square. If we substitute 2, we'll get minus 3.4. If we substitute 3, we will get minus 1.5, and then minus 0.85, then minus 0.54, and minus 0.36. So this is the energy of first orbit, second, third, fourth, fifth, and sixth. And sometimes in the question, if you know the difference of two energy level, then your time to solve the question will decrease. So do remember these value. For example, if I want to find the energy difference between the first and the fourth orbit, right? So it comes out to be how much? It will be 12.75. Now if I take the difference of the first two energy level, it comes out to be 10.2. So these values you can remember for hydrogen basically, right? Z will be 1. So then these are the values. Okay, right. Now let us see some of the illustrations or some of the previous year's questions based on the concept that we have studied in Bohr's postulates. The ratio for the speed of electron in the third orbit of helium positive to the speed of the electron in the third orbit of hydrogen atom will be. Okay, so what we have given, speed of electron in the third orbit of helium. So first of all, let us see the proportionality. So Vn is directly proportional to Z by n. And for helium positive, Z is equals to 2, and the orbit n is equals to 3. And for for hydrogen, Z is equals to 1 and n is equals to 3 in this case, no? Third orbit of the hydrogen. Okay, so we can say V1 by V2 will be equals to 2 by 3 divided by 1 by 3. So this comes out to be 2, and so the ratio will be 2 raised to 1, right? Option D. So what is excitation? So let us see. So we have given two energy levels. Let us say this is N1 and this is N2, and the electron is present in the lower energy level. Now if we say give this atom energy in the form of photons. Now we have a photon which is having energy which is equals to the difference in these two energy level. So electron will gain that energy and it will move to the higher energy level. Now the energy of this photon will be E2 minus E1, and E2 will be minus 13.6 if it is hydrogen, right? If I consider hydrogen atom, 13.6 minus 13.6, 1 upon 2 square, and this will be minus 13.6, 1 upon 1 square. So this will become 13.6, 1 minus 1 by 4. So like this, we can find the excitation energy. Now, what is ionization energy? Now, suppose the electron is present in the nth orbit. Now we want to remove this electron from the atom. So the minimum energy required to remove this electron from the atom is known as the ionization energy. Now let us say this is the limiting orbit, which means n tends to infinity. Now if we supply energy in the form of photon, then the energy required will be 13.6 by n square in electron volt. Right? So this is the ionization energy for an electron which is present in the nth orbit. So do remember this. An atom absorbs a photon of wavelength 500 nanometer and emits another photon of wavelength 600 nanometer. So electron is absorbing 500 nanometer and emits a photon of 600 nanometer. The net energy absorbed by the atom in this process is n times 10 raised to power minus 4 electron volt. The value of n is, okay, so assume the atom to be stationary during the absorption and the emission. We have to take the h value as 6.6 into 10 raised to minus 34 and a speed of light as 3 into 10 raised to power 8. Okay. Now let us calculate the energy of the photon. So here we have to use this formula. Hc by lambda is the energy of photon. So this formula we're going to use. So energy of the photon which is being absorbed, and let me call it as EA. So it will be 6.6 into 10 raised to power minus 34. C is 3 into 10 raised to power 8 divided by wavelength 500 into 10 raised to power minus 9. So this will be 19.8 upon 5 into 10 raised to power minus 34 plus 8 plus 7. So this is the energy of the absorbed photon. So I can further simplify this. So this will be 3.96 into 10 raised to power. This will be minus 26 plus 7 minus 19. Now it is in joules. So if I want to convert this into electron volt, I have to divide by the charge of the electron. So this will become 3.96 into 10 raised to power minus 19 upon 1.6 into 10 raised to power minus 19. So if you simplify this, so 3.96 divided by 1.6, so it comes out to be 2.475. 2.475 electron volt. Now let us calculate the energy of the released photon or emitted photon. So 6.6 into 10 raised to power minus 34, or you can say, since energy is inversely proportional to the lambda, so energy of the emitted photon divided by energy of absorbed will be lambda of the absorbed divided by lambda of the emitted. So energy of emitted will be lambda A, lambda of absorbed is 500 nanometer divided by 600 nanometer multiplied with 2.475 electron volt. Okay, so if you simplify this, so we have 5 divided by 6 times 2.475, so it comes up to 2.0625. 2.0625. Now let us take the difference of these two. So 2.475 minus 2.0625, right? So this comes out to be 2.475, so 0.4125. So which is nothing but 4125 into 10 raised to power minus 4 electron volts. So the answer of this question, so the n value will be 4125, right? Now let us see another illustration. So light of energy 12.75 electron volt is incident on a hydrogen atom in its ground state, and the atom absorbs the radiation and reaches to one of its excited state. The angular momentum of the atom in the excited state is x upon pi times 10 raised to power minus 17 electron volt second. The value of x, h value is given in electron volt second, and c value is also given. Okay, right. So The electron is in a lower energy state, and we have given some energy in the form of photon, and the energy of the photon is 12.75 electron volt, and by gaining this energy the electron move to a excited state from the ground state. So this is n equals to 1, and let us say this is n equals to n, right? Okay, right. So 12.75, this number sounds familiar, right? So let us see. It is the difference in these two energy level, right? 1 and 4. So we can say n is nothing but 4, because 13.6 minus 8.85 is nothing but 12.75 electron volt. So we know the electron will jump to the third excited state, or you can say the energy level will be 4. The angular momentum of the atom in the excited state is, so we know that angular momentum is given as nh upon 2 pi. So for fourth level, it will be 4h upon 2 pi. So this will be 2 times h upon pi, and h can be written as 4.14 into 10 raised to power minus 15 electron volt second divided by pi, and this will be 8.28 into 10 raised to power minus 15, which can upon pi, and this can be written as 828 into 10 raised to power minus 17 electron volt second divided by pi. So if we compare our result with this, we can see the x value is nothing but 828. So 828 is the answer, right? Now let us see the another concept. So what is de-excitation and the hydrogen spectrum? So de-excitation is when the electron jumps from a higher energy level to a lower energy level. So when electron jumps, then the photon is being released, and this photon will be having energy which is difference of these two energy levels. So E H minus E low, right? Right. So the spectral series, you must have studied this in chemistry. So let us quickly go through this. So when electron jumps to the ground state from the excited state, we can say we have a Lyman series. Say for example 2 to 1, from 3 to 1, 4 to 1, like this. Similarly, if the electron jumps from the first excited state, or n equals to 2, then we have Balmer series. And when it jumps from to the second excited state, which is n equals to 3, then we have Paschen. And then if the electron jumps from n for n equals to 4, then we have bracket series. And when it is jumping from an excited state to n equals to 5, we have Fund series. Now let us see how we can calculate the wavelength of different lines in these series. Now the first line corresponds to, we will call it the first line of the series, and the last line is known as the limiting line. So let us see. For Lyman, 1 by lambda is equals to r times 1 minus 1 by n square, where n is greater than 1. N can be 2, 3, 4. So if n is 2, we will get the first line. If n is infinite, we will get the last line, which is the limiting line. And there is one more formula you can remember. If I substitute r is the Rydberg's constant, which is 10 raised to power 7 meter inverse. So if I simplify this, I will get 912 angstrom divided by 1 minus 1 by n square. So you can remember this formula if you want to have an approximation, right? You can use this to have some approximated value of the wavelength. Similarly, in case of Balmer, 1 by lambda will be r times 1 by 2 square minus 1 by n square, and n will be greater than 2. And in Paschen, 1 by lambda will be r times 1 by 3 square minus 1 by n square, where n is greater than 3. And in bracket, 1 by lambda is equals to r times 1 by 4 square minus 1 by n square, where n is greater than 4. And in Paschen, 1 by lambda is r times 1 by 5 square minus 1 by n square. So with these formulas, we can find different wavelengths. Okay, so now let us quickly see the question. And one more thing I forgot to mention. Smaller the energy difference, greater the wavelength, right? So the first line will be the longest and the limiting line will be the shortest. So for limiting, gives us shortest wavelength, and first line gives us the longest wavelength. So do remember this. Now let us see the questions. In a hydrogen spectrum, lambda be the wavelength of the first transition line of the Lyman. So Lyman, right? So, and do remember one more thing, Lyman lies in the ultraviolet region and Balmer lies in the visible. Lyman, Balmer, Paschen, bracket, fund, right? So this lies in ultraviolet, Balmer lies in visible, and these three lies in infrared. Do remember this. So in a hydrogen spectrum, lambda be the wavelength of the first transition line of Lyman. So electron is coming from 2 to 1, first line of Lyman. So I can say 1 by lambda is equal to R times 1 minus 1 by 2 square. The wavelength difference will be A lambda between the wavelength of the third transition line of Paschen. Okay, so in Paschen, this is Paschen, right? So in Paschen, we have 1 by lambda is equals to R 1 by 3 square minus, this is the third transition, right? So third will be 4, 5, 6, 6 square, right? And second transition in Balmer. So in Balmer, we have 1 by lambda R 1 by 2 square minus 1 by 4 square, right? Now, let us say this is lambda 2, this is lambda 3, and this one is lambda 1. Oh, okay, let us keep it as lambda only, right? And we have given that the wavelength difference will be A lambda, right? So first let us calculate these values. So we have 1 by 9 minus 1 by 36. So this will be 3. So this will be 4. 3 by 36 times R, or we can say R by 12. And this will be R times 1 by 4 minus 1 by 16. So this will be 3R by 16. Now the difference of lambda 2 and lambda 3 is A lambda. So lambda 2 is 12 by R, or I can say it is 36 by 3R, and lambda 3 is 16 by 3R. Now the difference of these two is A lambda. So A lambda is lambda 2 minus lambda 3, which will be 36 minus 16 upon 3R. So this comes out to be 20 upon 3R, A lambda. And what is lambda? So lambda will be 4 upon 3R, right? So let us substitute the value. So A is equals to 4 upon 3R is equals to 20 upon 3R. So this 3R will get eliminated and we will get A as 5. So 5 is the answer. Now let us see one more concept. Suppose the electron is present in nth orbit, right? And let us say this is the ground state, n equals to 1. So we need to find how many possible different types of photons can be emitted when the electron de-excite from this excited state. So how many different spectral lines can be produced? So you should remember, for example, let me give you the illustration. Let us say the electron is in the 4th level. So this is second, this is third. So if electron is in the 4th level, then the electron can directly go to the 1st level, or the electron can go to the 2nd or to the 3rd. Suppose if the electron is in the 3rd level, it can directly go to the 1st level, or it can go to the 2nd level. So if the electron is in the 2nd level, it can go to, it has only one transition, that will be to the ground state. So how many lines are there? So it will be 3 plus 2 plus 1, so that will be 6. So you should remember, if the electron is in nth state, how many possible photons can be generated, different energy photons can be generated? It will be n into n minus 1 by 2. Right? So number of spectral lines. So do remember this formula. So if electron is in the fifth level, so it will be 5 into 4 by 2, so it will be 10, right? So here I conclude this video. So I hope the concepts and the derivation that you studied in this video are clear to you. See you in the next video. Thank you.